So in this question, it starts off by giving us a graph, and we can tell from the axes that this is a velocity time graph. Let's read through to find the context that fits this velocity time graph. We're told that this graph is of a sprinter who's running a 200-meter race in a straight horizontal track. The sprinter starts from rest, so starts from zero velocity, and accelerates uniformly until he reaches his top speed of 10 meters per second, and that takes 2.5 seconds. He maintains that speed for 17 seconds, so that takes us up to 19.5 seconds, when he experiences a cramp. So he's got muscle pain while he's running, and that's affecting the speed that he's running. We're told that he then decelerates uniformly, crossing the finishing line with a speed of u meters per second, and that's 22 seconds after the start of the race. Okay, we've got the context, we know the story, and we've got the graph. Looking at the graph, the only unknown is u, the speed or the velocity when he finally passes the finish line. Now, obviously, ideally in a race, you're running at your maximum capacity all the way until the end of the race. So he would have preferred to maintain his velocity of 10 meters per second, but the cramp got him and he slowed down slightly before crossing the finish line. What does the question ask us to do first? We are asked to calculate the distance covered by the sprinter up until the moment he experienced a cramp. Okay, so we know that a velocity time graph can be used to calculate displacement if we find the area underneath the graph. So that's what I'm going to focus on. Can I get an expression for the area underneath the graph in between the start of the race and the point where he experienced cramp? So from 0 seconds to 19.5 seconds. So here's just a portion of the graph. And I like to redraw my graphs, especially if I'm only focusing in on one part of the journey, rather than trying to label and annotate the one that's given to us. So for our particular phase of the journey, we know that the speed he gets up to is 10 meters per second. The length of time he's running is 19.7 seconds. The length of time he's running at the maximum speed is 17. And this is enough for us to get all of the dimensions of a trapezium. As long as I can calculate the area of this trapezium, I can then calculate its distance. So, formula for trapezium is going to be half the parallel sides added together, so the sum of the parallel sides multiplied by the distance in between them. Putting all of these in, we get a distance of 182.5 meters. So, because we can interpret the context and we know when the cramp occurred, we knew how much of the graph we had to focus on, and then it was really just a geometry question because we knew that the distance traveled would match the area underneath that graph. In part B of the question, we're asked to determine the value of u. Well, I know the distance traveled up until the cramp, and I know that the entire journey, the entire race, was 200 meters. That's the event that he was running. So there was another 17.5 meters to go. The rest of this graph should have an area of 17.5 meters. So let's go again with another sketch, this time just the second part of the graph, and we'll set the distance equal to 17.5. So that original speed was 10. It slowed down until a speed of u, and we know that the time was 2.5. This is still a trapezium, just one that's been rotated. It's changed orientation. So the formula is half times the sum of the parallel sides multiplied by the distance in between them. We're setting a distance of 17.5. And really from here, we're just going to tidy up and rearrange. So multiplying both sides by 2 and dividing by 2.5 gives us something very simple to rearrange. And we get a value of u that is 4 meters per second. In part C, we're asked to find the deceleration of the sprinter in the last part of the race. So we've got a lot of information. We now know the original speed in the last part of the race. We know the final speed that he crossed the finish line in the last part of the race. And we know the time that it took. That should be enough to find the deceleration. I could find the gradient. The gradient of a velocity time graph is the acceleration. Or I can rely on a Suva equation. And there's actually something very nice about those two techniques, which I hope you'll see as we work our way through. So let's collect our SUVAT variables. So we know the displacement is 17.5, that initial velocity is 10, final velocity of 4, and time of 2.5. So from here I want to choose a formula that I can use. I need to find A, and I have all of the other variables actually. So I have quite a few formulas to choose from. I'm going to go with V equals U plus A2, a straightforward choice. Substituting in the values that we know, 4 equals 10 plus 2.5a. Rearranging, we get negative 6 over 2.5. And this is going to lead to our answer. But if you have a look at what we said about the gradient, we have exactly the same calculation. The difference in the velocities, it went from 10 to 4, so that was negative 6. The difference in the time, it's gone from 19.5 to 22. That's a difference of 2.5 seconds. We've got exactly the same calculation, whether we chose the formula or we chose to use the gradient. In both cases, we get an acceleration of negative 2.4 meters per second squared. This runner was slowing down at a rate of 2.4 meters per second squared.